Let us discuss about the chemical reaction engineering problems asked in the GATE 2024. The question number 19, it states that the ratio of activation energy of a chemical reaction to the universal gas constant is 1000 Kelvin. The temperature dependency of the reaction rate constant follows the collision theory. Therefore, you have to find out the ratio of rate constant at 600 Kelvin to that of a 400 Kelvin. So, what is this collision state theory? See, the rate constant depends on temperature, right? Arrhenius theory states that the rate constant K is equal to Ka signifying the Arrhenius constant, pre-exponential constant suggested by Arrhenius, E into e power minus Ea by RT. Ea is the activation energy of the reaction. R is the universal gas constant and T is the temperature. And the reaction rate constant dependency with respect to temperature is T power 0, Arrhenius. So the collision theory suggests that the reaction rate constant will be equal to the pre-exponential constant for the collision theory into e power minus Ea by RT into temperature power half. So according to transition state theory, the reaction rate constant is pre-exponential constant of the transition state theory into e power minus Ea by RT into T. Arrhenius is T power 0, collision is T power half, transition is T power 1. So here we are supposed to use the collision state theory. So let us apply this particular equation in solving the problem. The given, let us assume that reaction rate constant at 600 degrees centigrade is nothing but Kc into e power minus Ea by R. Temperature is given as a 600 Kelvin into temperature power half is 600 power half. Similarly, if you wanted to find out the rate constant at 400 Kelvin is nothing but pre-exponential constant of the collision theory into e power minus Ea by R into, now the temperature is 400, into temperature power half, which is 400 power half. So in this question, the Ea by R is given as a 1000 Kelvin. That means you can substitute in place of Ea by R the 1000 Kelvin. Simply you have to take the ratio of K at 600 Kelvin divided by K at 400 Kelvin. If you take up the ratio and substitute the things, and you get the rate constant at 600 Kelvin divided by rate constant at 400 Kelvin is nothing but 2.816 around. Okay, this is what you have to take for the option number A. Thank you. Let us move to the next question. Let us discuss the question number 20. The question states that the rate of reaction of A gives rise to B is 0.2 mole per meter cube per second. That means the speed of the reaction is given at a particular concentration Ca1. That means at this particular concentration Ca1, the speed of or rate of the reaction is 0.2 mole per meter cube every second. The rate constant of a reaction at a given temperature is 0.1 meter cube per mole per second. That means the rate constant value for this particular reaction is given. So if the reaction concentration is increased to 10 times the Ca1 at same temperature, we have to find out the reaction rate. Okay, that means if you increase the concentration in a concentration to 10 times that of a Ca1, you are supposed to find out what is the speed or rate of a reaction. So rate of reaction at Ca1 is given as 0.2 mole per meter cube per second. Let us solve this. Let us assume there is some reaction happening in a container, which a container is consisting of the concentration of Ca1 is constant, which is the reaction is happening, A gives rise to B. So first of all, to apply rate, you have to find out what order is this reaction. So order of the reaction is not specified here, but the value of the rate constant is given as 0.1 meter cube per mole per second. So based on the units of the rate constants, you have to back calculate what order reaction is this. So let us do that. In any rate of reaction of a reactant which is A is denoted by minus RA. Minus is because A is getting consumed in the reaction, you have to take as a minus RA. Minus RA1, that is a case 1, is nothing but K into power Ca power N, okay, Ca1, okay, because the concentration is Ca1. What is rate of reaction of A? Nothing but dCa1 by dt, okay. So what is K from this equation? So divide this dCa1 A1 by dt with Ca1 power N. N is the order of the reaction. So what are the units of the rate constant? Concentration units are mole per meter cube, time units are in second, 1 by Ca power N, that means 1 by concentration power N, that is meter cube per mole power N. If N equal to 2, if you take the value of N equal to 2, the rate constant value will comes at K equal to mole per meter cube per second, meter cube per mole whole square. Finally, you get the value, the unit of the rate constant is in meter cube per mole per second. So the value is in 0.1 meter cube per mole per second. Okay, both the units are matching. If you take the order of the reaction is 2. So the given reaction A gives rise to B is nothing but a second order reaction. So in this rate of reaction, minus RA1 is equal to K into Ca1 power N, you have to take N equal to 2 here. So for the case 1, the rate of reaction is given. What is the concentration at the case 1 is nothing but Ca1. So minus RA1, which is the case 1, is nothing but K Ca1 square. In case 2, the concentration is increased by 10 times the Ca1. So what happens, that is case 2 is nothing but minus Ra2 is equal to K into Ca2 square, because the concentration in the case 2 is Ca2. Okay, the Ca2 is nothing but 10 times Ca1, we will deal it with the later. So if you do case 2 by case 1, minus Ra2 by minus Ra1, which is nothing K Ca2 square by K into Ca1 square. What is Ca2? It is given 10 times the Ca1 constant, Ca1. Okay, that means let us substitute the value in place of Ca2, 10 times the Ca1. So finally this Kk cancels out, Ca square cancels out, and finally 10 square, okay, into K, which is a point around a 0.2. So Ra2 is nothing but 0.2 times 10 square, which is nothing but 20 mole per meter cube per second. So the case 2 is given as, Kk got cancels out here. And finally we are left with 10 square. So finally what is Ra2? Minus Ra2 is nothing but, if you take this Ra1 to the right hand side, okay, Ra minus Ra2 is equal to minus Ra1 into 10 square. What is Ra1? A speed of the reaction for the case 1 is given as 0.2 mole per meter cube per second. So multiply the 10 square with 0.2, you get 20 mole per meter cube per second. So the answer is, the speed of the reaction for the case 2 is nothing but 20 mole per meter cube every second. So let us go to the new question. Let us start the question number 21. Here it is given two parallel first order liquid phase reactions. A gives rise to B and A gives rise to C. That means one of the molecules of A is giving to B and few of molecules of A giving to C. That means there are two products are forming from A, which are carried out in a well-mixed isothermal batch reactor. The initial concentration of A in the reactor is 1 kilomole per meter cube, while B and C, which are products of the reaction, the initial concentrations are 0. After 2 hours, which is reaction is happening in a batch reactor, after 2 hours, the concentration of A reduces to half of its initial value. Okay, and the concentration of B has become twice that of C. The rate, we have to find out the concentration of B, which finally the rate constant are K1 and K2 respectively. What we are supposed to find out here, the rate constant values, that is K1 and K2. Okay, this is what we are supposed to find out. Let us attempt that. Let us take these two reactions. A gives rise to B and A gives rise to C. The rate constant of the first reaction is K1, the rate constant of the second reaction K2. Then what is the speed of reaction of A? What is the rate of decomposition of A? Rate of reaction of A, which is denoted as minus A, which is minus dCA by dt. But minus is because the A is getting consumed, so that is why you have to take the minus symbol here. Because if it is only one reaction, it is simple K1 into Ca. Because A is consuming in the first reaction as well as A is consuming in the second reaction, the total reaction of A is combination of two reactions. So that is why you are supposed to take K1 into Ca, which comes from the first one, K2 into Ca, which comes from the second reaction. This is what the overall rate of reaction of A. Okay. What is, let us slightly deal with the things. Minus, let us take this equation, minus dCA by dt is equal to Ca into K1 plus K2. So minus dCA by dt by Ca, that means I am separating the concentrations on one side and the time terms on the other side. So minus dCA by Ca is equal to K1 plus K2 into dt. So let us integrate. If you integrate, that means everything happens in a batch reactor. Let us integrate the concentration, the initial concentration at time t equal to 0, the concentration is Ca0. At certain time t, the concentration is Ca. So if you integrate, you get the equation minus ln Ca, limits Ca0 to Ca, K1 plus K2, which are constants, which comes out of the integration, and integral dt is nothing but t, 0 to t. If you substitute the values of the limits, you get the final equation is minus ln Ca by Ca0 is nothing but K1 plus K2 into t. That means you have got one relationship in terms of K1 plus K2. That means finally you have to find out the values of the K1 and K2. So how you are going to find out? Get some equations to solve in terms of K1 and K2. So we have to take the help of the other things, because in the additional data that is given is after 2 hours the concentration of A reduces to half of its initial value and the concentration of B is twice that of C. That means they have provided the values of B and C, the formations of B and C. Okay, that means somehow in addition to decomposition of A, you have to consider what is the formation of B and what is the formation of C, so that you can able to use the concentration relationship given between B and C. So because B is the product in the reaction, we have to find out net rate of formation of B. The formations are positive, so Rb is the rate of formation of B, which is nothing but dCB by dt, because if you see the dCB by dt is nothing but K1 into Ca from this reaction. Similarly, net rate of formation of C is Rc, which is nothing but dCc by dt, because here the C is also the product, so product is taken as a positive, so Rc is equal to dCc by dt is K2 into Ca, because it is the rate constant for the C is K2. Now you have got the equations, and equation number 2 and equation number 3, you divide equation 2 by 3, you get dCb by dt by dCc by dt is nothing but K1 Ca by K2 Cb. Time term will be dt will get cancels out. Similarly, bring concentration of B terms on the left hand side and concentration of C terms on the right hand side, because Ca also will get cancels out here. Now to solve this differential equation, to apply the limits are the initial state to the final state. What is the initial concentration of B is nothing but Cb0 to the final concentration of B is Cb. Here the initial concentration of C is Cc0 and the final concentration of C is Cc. Between the limits, if you integrate, then it is a constant Cb minus Cb0 is equal to K1 by K2 into Cc minus Cc0. And it is already given the initial concentrations of B and C is 0. That means Cb0 and Cc0 are zeros. That is what it is given. So Cb by Cc is nothing but K1 by K2. You have got one more relationship in terms of K1 and K2. Our object is to find out using equation 1 and equation 4, you have to find out what are the values of K1 and K2. And it is provided here. Take the first equation. Okay, it is given after 2 hours. Okay, the concentration of A reduces to half of its initial value. That means Ca is equal to Ca0 by 2 after 2 hours. That means in place of T you put time. Okay, in place of Ca you put Ca0 by 2. Okay, and if you shuffle the things and if you apply that Ca0 will cancels out. In place of time you have to put either in terms of second, because everything is given in terms of hour. Okay, fine. T is also, you can take it in an hour. So from this equation 1 you get K1 plus K2 is equal to 0.346. Similarly, from this equation you get Cb, because given Cb equal to 2 times Cc. That means you can see the concentration of B after this 2 hours of the reaction is twice that of C. That is, Cb is nothing but 2 times Cc. Put the values in this equation, you get K1 by K2 is equal to 2 times Cc by Cc, which is equal to 2. And you get K1 is nothing but 2 times K2. Here one more equation, K1 plus K2 is nothing but 0.346. Using these two expressions, you can able to calculate the value of the K2, you get 0.1155 and K1 is 0.231. This is how you can able to find out this procedure to find out the answer. Okay, let us move to the next question. It is question number 44. It is given the first order heterogeneous reaction A gives rise to B is carried out using a porous spherical catalyst. Okay, that means heterogeneous reactions is talking about CRE2. Assume isothermal conditions and that given intraphase diffusion controls the reaction rate, because if you see in a catalyst where a reactant has to diffuse into the catalyst to get reacted, so sometimes the diffusion controls the process. That means how much speed the reactant goes into the catalyst, that defines the speed of a reaction. So given at bulk concentration of A, that means you can see because the reaction happens inside the catalyst, the concentration of the reactant outside the catalyst is different from the concentration of the reactant inside the catalyst. So the concentration of the reactant outside the catalyst is given 0.3 mole per liter. And actual reaction that is observed, that means the observed rate of reaction in a 3 mm diameter particle size catalyst is 0.2 mole per second per liter catalyst volume. That means given a catalyst volume, the speed of the reaction in this catalyst is 0.2 mole per second every liter per liter catalyst. So the bulk concentration of A is given 0.1 mole per liter. That means the concentration outside the catalyst is the 0.1 mole per liter. The observed rate of reaction in mole per second catalyst volume in a 6 mm diameter particle is, example, what they have given is two different cases they are given. In one case, if you keep the bulk concentration 0.3 mole per liter, that means if you maintain the concentration outside the catalyst 0.3 mole per liter, then the speed of the reaction is 0.2 mole per second per liter. And in the second case, for a 3 mm catalyst particle, that is case 1. The case 2 is, now they have changed the catalyst particle size, right, from 3 mm, example, it is given for a 3 mm particle. Suppose if I change the size of catalyst to 6 mm and initial concentration also I have changed, example 0.1, bulk concentration outside the catalyst is given 0.1 mole per liter, then what happens to the speed of the reaction? That means if I know the speed of reaction for a 3 mm particle, I have to find out the speed of the reaction for a 6 mm particle, given different conditions. And important observations and points to remember. Here it is given diffusion controls the rate. Two things will control the speed of the reaction. One is how fast the reactant is coming into the catalyst, and the second one is how fast it is getting reacted on the catalyst surface. These both control the things. Diffusion control, that means, or reaction control, given the things are diffusion control. What is this diffusion control means? Diffusion is slow. That means the molecules of A is taking lot more time to get into the catalyst and get reacted. So diffusion controls means whichever things is slow, that controls the process. Because the diffusion is slow, so entire speed of the reaction depends on that particular slow process. In other sense, if I say the diffusion is slow, in other words, reaction is fast. That means the reaction is happening very fast, but the thing is molecules are not coming onto the reactor surface as fast, okay, as compared to the reaction. So the given it is a first order reaction. Diffusion controls, that means the Thiele modulus of order 1, that means phi 1 square. Phi 1 is representing the Thiele modulus, okay, of order 1. Okay, the phi 1 square is called Thiele modulus. Okay, Thiele modulus is example high number. If Thiele modulus is high, that means the diffusion controls the process. Okay, if the Thiele modulus is high, what we can observe the things here? Most of the pellet surface is saturated with the surface concentration CAS. That means if the molecules are slowly coming onto the catalyst, into the catalyst, what happens, because it is slow, most of the surface is having saturated with CAS. If it is fastly consuming, the concentration will drop on the surface. Because the diffusion is very slow, entire surface is saturated with the high concentration, which is called as the surface concentration of the reactant A. So because it is already given that diffusion controls means most of the pellet surface is saturated with the surface concentration CAS. Bulk concentration will be equal to the surface concentration, because it is not getting reacted. The molecules of A is getting accumulated here. So Ca, bulk concentration of A, will be equal to the surface concentration, which is given as a 0.3 mole per liter, 0.3 mole per liter for the case 1. And the relationship between the speed of the reaction and surface speed and the actual speed. See the observed rate, that means observed rate means whatever you can able to calculate, okay, that is called the observed rate of reaction. Surface rate, because rate of reaction depends on the concentration. Surface concentration is high, that means speed of the reaction at the surface is high compared to the interior, because at the interior the concentration of reactant is very low, because A is slowly going into the reactor, into the catalyst. So how to relate surface rate with the actual rate? There is an equation that denotes observed or actual rate of reaction in the catalyst is nothing but eta times surface rate. Eta is denoting, okay, the effectiveness of the reactions or efficiency of the reactions, okay, effectiveness factor. So if you wanted to, if you know the actual speed, if you want to know the surface speed, you can able to relate the two things with this equation. What is the surface rate? Surface rate is, because it's a first order reaction, the rate of reaction at the surface is K1 into CAS, because reaction happens on the surface at a concentration of CAS. So the reaction speed on the surface is minus RA is equal to K1 into CAS. Then what happens to the effectiveness factor? Effectiveness factor is nothing but RA, actual speed inside the catalyst, divided by surface, okay, actual rate of reaction divided by rate of reaction on the surface. And for a first order cases, for a spherical catalyst particle, the effectiveness equation, if you follow the effectiveness factor derivation, you will get effectiveness factor is nothing but 3 by phi 1 square into phi 1 cot h phi 1 minus 1. This is a standard equation, you can able to remember this, the effectiveness factor, right? And it is already given diffusion is slow process. If the diffusion is slow, the Thiele modulus is very high. If the Thiele modulus is very high, phi 1 is very large. If phi 1 is very large, cot H phi 1 is 1. That is, if you put the number of phi 1 equal to 30, phi 1 equal to 40, and if you measure what is cot H 30, cot H 40, so these cot H phi 1 will be equal to 1. That means in this equation, you can put cot H phi 1 equal to 1. Because we are trying to simplify the things. This is the standard procedure you have to follow. Okay. When Thiele modulus is much greater than 1, that means if the Thiele modulus value is much higher than 1, then phi 1 minus 1 will equal to phi 1, because 1 is an insignificant number compared to the Thiele modulus. That means if you, example, Thiele modulus is 30, 40, 50, 100. So if you remove minus 1 from this Thiele modulus, it is not a great significant number. So instead of taking this one, remove this one. So when Thiele modulus is much greater than 1, so phi 1 minus 1 will equal to phi 1. So the final equation effectiveness factor is 3 by phi 1 square times phi 1, which is 3 by phi 1. So this is the equation we are supposed to use to estimate the value here. Effectiveness factor is nothing but 3 by phi 1. For a spherical catalyst, Thiele modulus can be defined in this way. Thiele modulus is R by 3 square K1 by dE. K1 is the reaction rate constant, dE is effective diffusivity, and R is the radius of the pellet. Okay, if you know all these numbers, you can able to calculate the Thiele modulus. Minus Ra is nothing but K1 into CAS. I mean, these kind of substitutions you can able to do. Minus Ra is nothing but 3 by R into square root of dE K1 into CAS. How we got this number? So because I know that minus Ra equal to effectiveness times minus RAS. What is minus RAS? Minus Ra is nothing but K1 into CAS. Okay, effectiveness factor is nothing but 3 times divided by phi 1. What is phi 1? Is nothing but square root of R by 3 whole square into K1 by D. If you substitute everything, finally the rate of reaction is nothing but 3 by R square root of dE into K1 into CAS. So final, this is the rate you are going to use to solve the problem. What is the case 1? Case 1, the diameter is a 3 mm. Case 2, the diameter is the 6 mm. What is concentration? When the diameter is 3 mm, what is the concentration they have used is 0.3 mole per liter. When it is a 6 mm, what is the concentration they have used? Okay, around 0.1 mole per liter. So rest everything will be same. The reaction is the same, so rate constant value will be the same for the case 1 and case 2, and effective diffusivity is the same for the case 1 and case 2. What is the thing that is going to change is radius and the concentration. For the case 1, you have to take the radius 1 and concentration 1. For the case 2, you have to take radius 2 and the concentration 2. If you do it the case 2 by case 1, you get minus Ra2 by minus Ra1 is R1 by R2, CAS2 by CAS1. Okay. If you plug in all the numbers, because you know rate for the case 1, you know radius of the pellet for the case 1, radius of the pellet for the case 2, the concentration for the case 2 divided by concentration for the case 1. Finally, your answer, the speed of the reaction for the case 2 is 0.033 mole per second per liter. This is the answer you are supposed to get. So I recommend you to remember few equations, because most of the questions asked through this kind of first order systems, effectiveness factor, and spherical catalyst, the Thiele modulus, what is effectiveness factor, what is Thiele modulus, what is rate, how to relate, and actual rate and the surface rate. These are the standard the questions that is going to ask. It is better you remember this to solve this particular problem. Thank you. Let us move to the next question. Let us move to the question number 45. In question number 45, it is asked, a first order liquid phase reaction A gives rise to B is carried out in a 2 isothermal plug flow reactors of volume 1 meter cube connected in series. The feed flow rate and concentration of A to the first reactor is 10 meter cube per hour. Volumetric, these are given. Volumetric flow rate and concentration is 1 kilomole per meter cube. At steady state, the concentration of A exiting the second reactor, that means in the second reactor, is 0.2 kilomole per meter cube. Okay, this is what the situation is given. The two PFRs of equal volume, 1 meter cube, 1 meter cube, which are connected in series. It's a given, it's a first order reaction. A gives rise to P. Okay, this situation is provided. Okay, if two PFRs are replaced with two equal volume CSTRs, that means if I replace these two with the two CSTRs, given the conditions, initial concentration is the same, final exit, okay, let us put two concentrations to achieve same overall steady state conversion. That means whatever may be the concentration exiting the reactor, that means a conversion you are expecting from these two reactors, you also expect the same conversion. For that case, if you want to expecting the same conversion as that of a two PFRs, then what could be the volume of the PFRs? What could be the volume of the CSTRs? So we have to find out V1 and V2. Okay, V1, V2 are the same. Okay, let us start. Given two PFRs in series, and if you remember, two PFR series of 1 meter cube each, it is the conversion coming from these two PFRs which are connected in series, which is same that of if it is a 1 PFR of 2 meter cube volume. Okay, that means you connect, instead of connecting these two, make a only 1 PFR which is of the volume of 2 meter cube. So same conversion you are going to get. So this is the case 1. Ca0 is initial concentration, volumetric flow rate nu 0, molar flow rate is Fa0, and exit concentration is Ca. Nu 0 is the exit volumetric flow rate, and Fa0 is the molar Fa. This is not Fa0, this is Fa. Okay, this is Fa, exit concentration, exit molar flow rate. Okay. Oh, you know, volume of the PFR. Okay, which is nothing but Fa0 into 0 to x dx by minus Ra. And you can also use the another equation, which this is in terms of conversion, this is in terms of concentration. Volume of the PFR is nothing but volumetric flow rate of the reactor into integral Ca, final concentration to initial concentration, dCA by minus Ra. Okay, this either you can use this equation or this equation. So because this equation a bit easy, because I have to deal with the concentrations. If I have to deal with the conversion, I have to convert everything in terms of conversion. Here directly minus Ra equal to Kca, I can directly integrate if the reaction rate is expressed in terms of concentration. So given minus Ra equal to Kca, because it's a first order, let us substitute in place of minus Ra equal to Kca. Volume of the PFR is nothing but volumetric flow rate divided by K, from Ca to Ca0, 1 by Ca into dCA. I know integral 1 by x dx is ln. Okay, volume of the PFR, if you substitute the limits, finally you get volume of PFR is equal to nu 0 by K into ln Ca0 by Ca. So you know everything. Okay, volume of the PFR 2 meter cube, you know. Ca0, it is given 1 kilomole per meter cube. Ca, that means it is also given the concentration of A exiting the reactor is 0.2 kilomole per meter cube. So everything is provided. You have to find out the rate constant value K. Okay, the rate constant value K, if you substitute the all numbers, you get 8.047 per hour. Okay, okay, that means from the case 1 for the PFR, you could able to found out the rate constant of the reaction, which is 8.047. Let us use this rate constant value for the case 2 to find the volume of the CSTRs. And every conditions remains the same. Ca0 is the same. Ca2 will be the same as that of a PFR. That means they're expecting the same conversion from both the reactors. So volume, because these two CSTRs are of equal volumes are connected in series. Okay, we have to find out what is V1 and V2. If you found out V1, which is the same as the volume as a V2, because two are equal sized. So if you remember the equation, if n CSTRs are connected in series, the exit concentration after nth reactor you can able to find out. Ca0 is the initial and Can is the final reactor, nth reactor. So Ca0 by Ca nth reactor is nothing but 1 plus k tau whole power n. N is representing number of reactors in series. Here it is given that there are two reactors connected in series. The value of the n will be taken as a 2. So 1 plus k tau, if you rearrange this equation, Ca0 by Ca n power 1 by n. So tau is nothing but volume by volumetric flow rate. So the volume is encrypted in the value, expression for tau. Tau is the space time, which is volume by volumetric flow rate, is nothing but Ca0 by Can power 1 by n minus 1. Here n equal to 2. I know Ca0, I know Ca, I know K from the first case. So you can able to get volume of reactor. Any one reactor is 1.536 meter cube. V is the volume of every CSTR, right? So this is how you can able to find out the answer. Let us move to the next question. The question number 46. It is given the resident time distribution E for a non-ideal reactor is given in the figure. A first order liquid phase reaction with a rate constant of 0.2 per minute is carried out in a reactor. For an inlet reactant concentration of 2 mole per liter, the reactant concentration at the exit, that means there is a reactor, non-ideal reactor, it could be any reactor with PFR, CSTR, anything is comes under the non-ideal reactors. If that is the case, if I use the initial concentration of example, how much? 2 mole per liter is my initial concentration to the reactor. What could be the exit concentration? That means they wanted to find out the conversion in the reactor. Okay. The reacted concentration in the exit stream. So from this you can able to calculate exit concentration. Don't worry, I will let you know. And the simplest non-ideal model for a given conditions is segregated model. Using segregated model, you can able to find out with the information of E, okay, residence time distribution curve. This is the residence time distribution graph that is provided. Using this graph and segregated model, you have to find out what is the conversion. In segregated model, the final conversion from the reactor, because if you remember in the segregated model, and there are small batch reactors, because reaction happen inside the reactor in the form of small batch reactors. Okay, that means you have to find out the conversion, okay, in the different batch reactors inside the reactor. That means reactant molecules will lump together to form a batch. So the conversion in the each batch is different. Why it is different? Because every batch reactor is spending different time in the reactors. So finally you have to take average of, because every batch reactor, that means every circle inside this reactor is a batch reactor. What is the final conversion? You have to average out the conversions in all these batch reactors. So that batch reactor model is here. The final conversion exiting the reactor is integral 0 to infinite x of t into e of t dt. What is x of t? The conversion in every batch reactor. Okay. E of t is the residence time distribution of these batch reactors, other molecules, you can say that. And I know it's a kind of liquid phase reaction. The concentration of A is equal to Ca0 into 1 minus x. Therefore x, that means a batch reactor in the conversion is 1 minus Ca by Ca0. That means in place of x you can substitute 1 minus, let us go together. And this is how the concentration and conversion things. So because inside is every circle is a batch reactor, what is the time? Let us calculate the time. Okay, conversion from the batch reactor. X of t is the conversion from the batch reactor. So what is t? Okay, let us find out the equation for the batch reactor. The equation for the batch reactor is the time of a batch reactor is nothing but integral Ca to Ca0 dCa by minus Ra. And because this is the equation for the batch reactor, integral Ca to Ca0 dCa by, because of first order I replace minus Ca with Kca, which is nothing but 1 by K into ln Ca with up to limits Ca to Ca0. So from this I can able to find out that t equal to 1 by K into ln Ca0 by Ca. Therefore what is Ca by Ca0 is nothing but e power minus kt. Therefore x, which is nothing but 1 minus Ca by Ca0, which is nothing but 1 minus e power minus kt. Okay, that means the x term, Okay, I have got what is how my conversion in the every batch reactor is 1 minus e power minus kt. Let us get the equation for the e of t, so you can combinedly integrate using the segregation model. And this is the residence time distribution graph, right? And it is given, it's a kind of between the time 3 and 5 the molecules are spending a time. Okay, the information is between 3 and 5 molecules are spending inside the reactor. So that is what the residence time distribution. And let us assume the height, this is h, because you have to find out the area under the curve. Okay, first of all, and area under the curve. Okay, to find out the height you have to find out the area under the curve. What is this area under the curve? E, with E on y axis and time on x axis. Area under the curve is between the limits 3 to 5. You have to find out E of t dt. That means E of t dt means area under this curve between the limits 3 to 5. And you know it's a kind of a rectangle. What is a rectangle area? That means area is nothing but height into 2. That means this distance is 5 minus 3, which is 2. H is assumed as h. I mean this height is assumed as h. So area is nothing but h into 2, which is equal to 1. That means area under the any residence time distribution curve should be equal to 1. So the area which is under this curve, which is equal to 1. From this, the value of h is equal to 1 by 2. Okay. Then what is the value of h? That means between 3 to 5, the value of E of t is h. Okay, this is the height. That means E equal to half. That means this point on the y-axis is half. That means I got the value of E of t, which is half, and I know the equation for x of t, which is 1 minus e power minus kt. Simply I substitute these two in this segregation model and I evaluate that what is the average concentration of all the molecules exiting the reactor. So if you integrate, that means you can see 1, if you integrate to 1, it is time, and integration of e power minus kt is nothing but e power minus kt by minus 1. So this minus 1 will become plus. And if you apply the limits, you get the conversion in the reactor. In this particular reactor, molecules exiting is 92%. So this is how we can estimate. It could be any reactor, it could be CSTR, it could be PFR, anything can be modeled using segregation model. So this is the conversion. But in the question, what we are supposed to find out? Reactant concentration in the exit stream. If you know the conversion, how you can able to find out the reactant concentration in the exit stream? That Ca, okay, is equal to Ca naught into 1 minus x. Okay. You know Ca0, which is given. You know x, 92%. You can find out the exit concentration. So please find out on your own. And let us move to the next question. This is very interesting question, the question number 62. It's a kind of biochemical reaction happening inside this reactor. Okay, this is a chemostat. Chemostat is a reactor where biochemical reactions happens. And if you see the reactor, there is the product which is coming out of the reactor, and few part is again recycled back to the reactor. And in general, I will explain you what is happening in this reactor is cells are forming. In the biochemical reactions, the substrate, that is feed will be consumed and more cells will form in the reactor because it's a biochemical reaction. That means in this reactor, the substrate is getting consumed and cells will get formed. So the conditions are given that you can see once the product cells are getting formed and it is go to the cell concentrator. This cell concentrator, that means there are two streams that is coming from the cell concentrator. In one stream, okay, cells are not removed. Okay, cells are removed in the concentrated shell. In this stream, that is CS2 and CS1, which is a concentration of substrate exiting this concentrated cell is CS1. The concentration of cells exiting the concentration, this cell, is CS2. What is the job of this particular concentration, cell concentrator? the whatever the cells that has been formed in the reactor, again it has sent back to the some of the cells is sent back to the reactor. Okay, because cells will consume more feed to form even more cells. So cells are important. Okay, that is why the job of the cell concentrator is to send more amount of cells into the reactor back again by concentrating in the cell concentrator. And you can see that if you see the stoichiometry, if you see the mole balance or mass balance of the reactor, we have to somehow do the mass balance at the center, this highlighted portion in the circle. Why, I will explain you in this example. A chemostat with a cell recycle, okay, this is called cell recycle because we are sending the feed flow rate and culture volume are given. As culture volume means volume of the reactor is given by 200 liters. The feed flow rate that is going into the reactor F from one stream is 75 liter per hour. The glucose concentration in the feed is CS0, which is 15 gram per liter. That means glucose is a feed for the cell. The initial concentration of the glucose is 15 gram per liter here in the stream. Okay, assume monode kinetics and a specific cell growth rate. That means how much speed the cells are forming in the reactor is given in terms of monode kinetics. Okay, this is called the equation, that is speed of the cells formation is given. And inside this mu m Cs by Ks plus Cs. Okay, Cs is the substrate concentration in the reactor and Ks is a monode there is a specific constant for the monode kinetics. Assume maintenance and death rates to be 0. That means no cell is is getting died in the reactor. That means don't worry, it is not of a major concern. And input feed is sterile. Sterile in the sense means there is free of cells. Sterile means initial concentrations of cells which is going into the reactor is equal to 0 in this particular stream. The glucose concentration in the recycle stream is CS1. That is means after the reaction few amount of glucose will get consumed. After glucose getting consumed, few glucose whichever is remained in the outlet stream, which is called CS1. So this is the situation is given. You have to find out CS1. That means what is the glucose concentration is left in the reactor. Okay, that means CS1 is there in the inner loop. So you can able to concentrate on this particular circle. If you do the mass balance or mole balance in this particular loop, you can able to find out the CS1, which is concentration of glucose exiting the reactor. That is what we will solve one by one. Before that, what is given, that is most important. Here the speed of cell formation in this reactor is given. dCc by dt is nothing but speed of formation of the cells in the reactor. Because the information is given with respect to cells, you have to do first mole balance on the cell of the reactor, because you can do the mole balance on the substrate, that is, this is glucose, or you can do the mole balance of the cell. Because the speed of reaction of the cells are given, if you do the mole balance with respect to cells. Okay, let us do it, because a bit elaborated version. And you can see, this is the same picture. F is the feed stream, and because it's a recycle stream, and recycle, how much recycle stream is also already provided. You can see F is the feed, volumetric flow rate of the feed that is coming into the reactor, and alpha is the recycle ratio. That means how much amount of F that is coming out of the reactor is getting again recycled back, and that is what it is given. Alpha is the recycle ratio. Recycle ratio means that alpha, the part is 0.5 is given, and the cell because the cells which comes exiting the reactor after a cell concentrator, this stream is enhanced by more cells, because the job of the cell concentration to increase the concentration of the cells. So how much cells that concentrated compared to the exit stream of the reactor is beta times CS1. So beta is the concentration factor. So beta is 2. That means After the cell concentrated, the concentration of cells is doubled compared to the which comes exiting the reactor. So given this scenario, we have to find out the value of CS1 here. Let us find a small approach. Okay. Here the cell is our product, substrate which is glucose is our reactant. And you can do rate of two things. Either you do the mole balance on the substrate or you can do the mole balance on the cell, because the information of the speed of the reaction of the cells is given. Better to the mole balance for the cells. So what is the speed of the reaction? The speed of the reaction is nothing but dCc by dt, which is positive because cells are formed in the reactor. You should not take the negative symbol here. So Rc is the rate of formation of the cells in the reactor, which is dCc by dt. I mean DC1. Okay, the concentration of the cells in the reactor is Cc1. Okay, you have to take Rc in the reactor is dC1 by dt. So what is dCc by dt is nothing but given mu g times Cc. Okay, it is already given. How this is given? You can see this dCc by dt is nothing but mu g times Cc. What is mu g? Mu m into Cs by Ks plus Cs. Okay, let us do it. Mu g is nothing but mu m into Cs by Ks plus Cs. Volume is given, flow rate is given, initial concentration of the glucose is given, mu m is given, Ks is given. Okay, initial sterile feed, that means the concentration of cells, this inlet in this particular stream is 0. Let us do the mole balance now. Mole balance on the cell in this dotted, in this circle. Mole balance in minus out plus generation minus consumption. You can don't need to take it because cells are not consumed, cells are formed. So inlet minus outlet plus generation is equal to accumulation. Because a reactor is operated at steady state, the accumulation term will be 0. What is in? How many ins are there? There are 2 ins. One from the first stream, second from the second stream. So inlet is F times CCO. That is what? The mole balance. How many moles of entering into the particular reactor? F times CCO. And the another stream, right? How many? Volumetric flow rate. In fact, how many alpha times F is coming into the second stream? So what is the concentration of cells in the second stream? Is nothing but beta times Cc1. So total inlet is from the stream 1 and plus in the stream 2. What is out? That is, you can see there is only one exit here. So what is the out? That means how much amount of mole balance out? 1 plus alpha times F. Okay, 1 plus alpha times F into Cc1. What is the generation? Okay, I know inlet, I know exit. How much amount of cells are getting formed in the reactor is nothing but rate of reaction of the cells into the volume of the reactor. I know rate of reaction of the cells, which is nothing but Rc into V. Rc is nothing but mu g into Cc1. Why you have to take Cc1? Because the concentration of the cells in the reactor is Cc1 times V. Okay, F is the flow rate here. Okay, imagine. Okay. And let us do, if you apply all the things in this mole balance, finally you get an expression, right? Mu g is F by V, 1 plus alpha minus alpha times beta. I know everything. I know F, I know V, I know alpha times beta. So everything is given. If I put in this particular expression, I got mu g is equal to 0.1875. What is mu g? Mu g is given mu m into Cs1 by Ks plus Cs1. So everything I know except Cs1, the concentration of substrate that is exiting the reactor. Mu m Cs1 by Ks plus Cs1, which is 0.1875. Okay, therefore the Cs1, if you calculate, you get Cs1 is nothing but 3 gram per liter. That means the final answer, the concentration of the cells exiting the reactor is 3 gram per liter. Just a small update. Here F, right, it is called liter per hour, volumetric flow rate. Okay, it's not a molar flow rate, it's a volumetric flow rate. Otherwise units will not get cancels out. F is the, the unit in liter per hour, concentration is in the units of mole per liter, and if you both cancels out, you get mole per hour. So finally the mole balance, everything should be in mole per hour. That means in should be in mole per hour, out should be in mole per hour, generation should be in mole per hour. Okay, so small correction, the F is not a molar flow rate, it's a volumetric flow rate in this particular example. Thank you, meet you with the next lecture.